Welcome! In this session, we'll explore a fascinating problem from the world of algorithms, problem number 1911, maximum alternating subsequence sum. Together, we'll analyze the problem, consider different approaches, and break it down step by step. Let's dive in and sharpen our problem-solving skills. In this problem, we are given an integer array called nums, and our goal is to find the maximum alternating sum of a subsequence. Now, an alternating sum is calculated as the sum of the elements at odd indices, minus the sum of the elements at even indices, where the indices are considered 1-based. For example, if we have a subsequence, 4, 2, 5, 3, the alternating sum would be the sum of the first and third elements, which are 4 and 5, minus the sum of the second and fourth elements, which are 2 and 3. That gives us 4 plus 5, 2 plus 3, and the result is 4. The challenge here is to determine the maximum alternating sum we can achieve by optimally choosing a subsequence from the array. Remember, a subsequence is formed by deleting some or no elements from the array while maintaining the order of the remaining elements. The input constraints state that the array can have up to 10⁻5 elements, with each value between 1 and 10⁻5, so efficiency is key. The output will be a single integer, representing the maximum alternating sum achievable. Let's look at some examples to understand this better. In the first example, the input array is 4, 2, 5, 3. One possible subsequence is 4, 5, 3. If we calculate the alternating sum for this subsequence, we add the first and second elements, which are 4 and 5, and then subtract the third element, 3. This gives us 4 plus 5, 3 equals 7. After exploring all possible subsequences, we find that 7 is the maximum alternating sum for this input. Now for the second example, the array is 5, 6, 7, 8. Here, the optimal subsequence is simply 8. Since it consists of just one element, the alternating sum is equal to that element, which is 8. Including any other element from the array would actually decrease the alternating sum, so the answer remains 8. In the third example, the input array is 6, 2, 1, 2, 4, 5. For this input, one possible subsequence is 6, 1, 5. The alternating sum is calculated as the sum of the first and third elements, which are 6 and 5, minus the second element, 1. This results in 6 plus 5, 1 equals 10. After examining all possible subsequences of the array, we find that 10 is the maximum alternating sum we can achieve. These examples highlight the importance of carefully selecting which elements to include in the subsequence to maximize the alternating sum, while keeping the order intact. Now, let's summarize some key points and edge cases to keep in mind. First, if the array contains only one element, the maximum alternating sum is simply the value of that element. Additionally, if all elements in the array are the same, the maximum alternating sum is still just the value of a single element, because including any other element would not increase the sum. Another critical consideration is efficiency. Since the input array can have up to 10⁻5 elements, our solution must be designed to handle this size efficiently. Finally, remember that you have the freedom to skip elements in the array to form an optimal subsequence. This flexibility is key in achieving the maximum alternating sum, and the challenge lies in determining the best way to make these selections. To begin, let's explore the brute force approach to solving this problem. The core idea here is to compute the alternating sum for every possible subsequence of the array. In implementation, we would generate all subsequences, calculate their alternating sums, and find the maximum among them. While this approach is conceptually straightforward, its time complexity is prohibitive. Generating all subsequences alone requires O2 to the power of n time, and calculating the alternating sum for each adds further overhead. As a result, this approach becomes infeasible for larger input sizes due to its exponential nature. While it's a useful theoretical tool to understand the problem, it lacks practicality for real-world applications where efficiency is critical. Now, let's move to a more efficient solution using dynamic programming. The key observation here is that at any position in the array, we have two choices: include the current element in the subsequence or skip it. If we include it, its impact on the alternating sum depends on whether it contributes to the odd or even group in the sequence. To formalize this, we define two states, dp_odd and dp_even. dp underscore odd tracks the maximum alternating sum up to a given index when the last included element belongs to the odd group, while dp underscore even does the same for the even group. With this framework, we can derive the transition equations. For instance, if we include the current element in the odd group, we take the maximum of the previous dp underscore odd state or the dp underscore even state plus the current value. Similarly, for the even group, we subtract the current value from the previous dp underscore odd state. By iterating through the array and updating these states, we can compute the result efficiently in O(n) time. However, this approach requires O(n) space to maintain the two arrays, which can still be optimized further. To address the space usage, we can refine the dynamic programming approach by observing that each state only depends on the previous one. This means we don't need to maintain full arrays. Instead, we can use two variables, prev underscore odd and prev underscore even, to represent the previous states. As we process each element, we update these variables iteratively. This modification retains the O(n) time complexity while reducing space complexity from O(n) to O(1). By eliminating the need for extra memory, this approach becomes the most memory-efficient solution. Despite its simplicity, it delivers the same results as the standard dp method, making it an optimal choice for both time and space efficiency. The space-optimized dynamic programming approach emerges as the best strategy for solving this problem. The brute force method, while intuitive, is computationally prohibitive due to its exponential time complexity. Standard dynamic programming significantly improves efficiency with a linear time complexity of O(n), but it still requires O(n) space for the dp arrays. By refining this further to use only two variables, the space-optimized dp approach achieves the same time efficiency while reducing space usage to O(1). This makes it the most scalable and efficient solution. The key breakthrough lies in recognizing that alternating sums can be represented through two states, odd and even, which simplifies the problem into manageable subproblems. Transitioning to a space-optimized solution was a straightforward yet impactful improvement that ensures the approach is both practical and scalable for real-world use. Finally, while the space-optimized dp approach is the most efficient solution, it's worth noting the trade-offs and alternatives. For beginners, the standard dp method may be easier to grasp due to its explicit use of arrays, which clearly illustrates the transitions. The brute force approach, though impractical, is valuable for building intuition and serves as a foundation for understanding more advanced techniques. Ultimately, the space-optimized dp method strikes the ideal balance between simplicity, efficiency, and scalability. It not only meets the problem's requirements but also highlights the power of optimization in dynamic programming, making it the best solution for this problem. To solve the problem of finding the maximum alternating sum of a subsequence, we first need to understand what an alternating sum is. In this context, the elements of the subsequence alternate between being added and subtracted. For example, if the subsequence is a, b, c, the alternating sum would be calculated as a, b plus c. The key challenge here is to determine the optimal subsequence that maximizes this alternating sum, but without explicitly generating all possible subsequences. Generating all subsequences would be computationally expensive due to the exponential number of possibilities. Instead, we can plan an efficient approach using dynamic programming. The core idea is to maintain states that represent the maximum alternating sum at a specific index, depending on whether the last operation was an addition or subtraction. This allows us to systematically calculate the result while considering all possible subsequences implicitly. To formalize this, we define two states, dp I0, which represents the maximum alternating sum ending at index I with a positive sign, and dp I1, which represents the maximum alternating sum ending at index I with a negative sign. Now, we define the transition relations that govern how these states are updated as we process each element in the array. If we decide to add the current element with a positive sign, the value of dp I0 is determined as the maximum of two options: either we keep the previous subsequence ending with a positive sign, dp I1 0, or we extend a subsequence that previously ended with a negative sign by adding the current element a underscore I. Mathematically, this is expressed as dp I0 equals max dp I1 0 dp I1 1 plus a underscore I. Similarly, if we decide to add the current element with a negative sign, the value of dp, I1, is updated as the maximum of either keeping the previous subsequence ending with a negative sign, dp, I1, 1, or extending a subsequence that ended with a positive sign by subtracting a underscore I. This is written as dp, I1 equals max, dp, I1, 1, dp, I1, 0, a underscore I. At the start, we have a simple base case, at index 0, dp, 0, 0, is equal to the first element a underscore 0, since the only valid subsequence is the single element itself, and dp, 0, 1, is 0, as no subsequence can begin with a subtraction. Using these relations, we compute the states iteratively by traversing the array from the first index to the last. After completing the iterative computation, the result we are looking for is the maximum value between dp, n1, 0, and dp, n1, 1, where n is the size of the array. This is because the maximum alternating sum can end either with a positive or a negative sign, so we take the larger of the two possibilities. To optimize the space complexity, we can observe that at any given point, we only need the previous state to compute the current state. This means we do not need to maintain the entire 2D dp table. Instead, we can use two variables, prev_positive and prev_negative, to store the last computed values. This reduces the space complexity from O(n) to O(1), while still preserving the correctness of the solution. The key insights here include the efficiency of the dp approach, which avoids the brute force method of generating all possible subsequences. By representing the problem in terms of states, we ensure that every possible subsequence is considered implicitly, without the need for exponential computations. Additionally, the space optimization highlights how we can reduce memory usage by leveraging the fact that only the last state is required for the current computation. To implement the algorithm, we can use either a 2D dp array or the optimized version with two variables. If using the dp array, it will store dp, I0, and dp, I1, to represent the maximum alternating sums ending at index I with a positive or negative sign, respectively. In the optimized version, we replace the array with two variables, prev_positive and prev_negative, which track the states for the previous index. In terms of complexity, the time complexity of this approach is O(n), as we only iterate through the array once and perform constant time operations at each step. The space complexity is O(1) when using the optimized version with two variables, or O(n) if we use the full dp table. This combination of linear time and constant space makes the algorithm highly efficient and scalable, even for large input arrays. This solution adopts a dynamic programming approach to solve the problem efficiently. The goal is to calculate the maximum alternating sum of a subsequence of the input array. First, we initialize two variables even and odd to 0. These represent the maximum alternating sum achievable when the last element added to the subsequence is at an even index or an odd index, respectively, in terms of the alternating sequence. We iterate through the input array in reverse. At each step, we update even and odd based on the current element and the previously computed values. Specifically, even is updated to the maximum of its current value and the sum of the current element and odd. Similarly, odd is updated to the maximum of its current value and the difference between even and the current element. Finally, the result is stored in even, as it represents the maximum alternating sum when starting from an even position, the first element of the subsequence. The time complexity of this solution is O(n), as we traverse the array once, and the space complexity is O(1), as we use only two variables to store intermediate results. This is the Java implementation of LeetCode problem number 1911, maximum alternating subsequence sum. The logic mirrors the Python solution, using two variables to track the maximum sums for even and odd states while traversing the array in reverse. Key differences include Java's explicit type declarations and usage of math.max for comparisons. The method returns the maximum alternating sum as a long, ensuring compatibility with larger values. To solve the problem, let's look at the first example where nums is 4, 2, 5, 3. The initial setup involves determining the length of the array, which is 4, and initializing two variables, even and odd, both set to 0. These variables will track the maximum alternating subsequence sum where the last included number is at an even index or an odd index, respectively. Starting from the last element of the array, we process each number one by one. In the first iteration, at index 3 where the value is 3, we update the even variable to the maximum of its current value and the sum of odd plus the current number, resulting in 3. The odd variable is updated to the maximum of its current value and the difference between even and the current number, which remains 0. At this point, even is 3 and odd is 0. Moving to the next iteration at index 2, where the value is 5, we perform similar updates. Even becomes the maximum of its current value and odd plus the current number, which updates it to 5. Odd remains 0. Now, even is 5 and odd is 0 after this step. Next, at index 1 where the value is 2, we calculate the updates for even and odd. Even remains 5 as it is the maximum of its current value and odd plus the current number. Odd is updated to the maximum of its current value and even minus the current number, resulting in 3. At this stage, even is 5, and odd is 3. Finally, at index 0 where the value is 4, we compute the last updates. Even becomes 7, the maximum of its current value and odd plus the current number. Odd remains 3, as it is the maximum of its current value and even minus the current number. After processing all elements, the final values are even as 7 and odd as 3. Therefore, the maximum alternating subsequence sum for this example is 7. Let's analyze the second example with nums equal to 6, 2, 1, 2, 4, 5. The array length is 6, and we initialize even and odd to 0. Starting with the last element at index 5, which is 5, we compute even as 5, the maximum of its current value and odd plus the current number. Odd remains 0, as it is the maximum of its current value and even minus the current number. At this point, even is 5, and odd is 0. Moving to index 4, where the value is 4, even remains 5, as it is the maximum of its current value and odd plus the current number. Odd gets updated to 1, the maximum of its current value and even minus the current number. At the end of this iteration, even is 5, and odd is 1. Next, at index 3 where the value is 2, we calculate the updates for even and odd. Even remains 5, as it is the maximum of its current value and odd plus the current number. Odd gets updated to 3, the maximum of its current value and even minus the current number. Moving to index 2, where the value is 1, even remains 5, as it is the maximum of its current value and odd plus the current number. Odd becomes 4, the maximum of its current value and even minus the current number. At index 1, with the value of 2, even is updated to 6, the maximum of its current value and odd plus the current number. Odd remains 4, as it is the maximum of its current value and even minus the current number. Finally, at index 0, where the value is 6, even becomes 10, the maximum of its current value and odd plus the current number. Odd remains 4, as it is the maximum of its current value and even minus the current number. After processing all elements, the final values are even as 10 and odd as 4, making the maximum alternating subsequence sum 10. In the third example, nums contains just one element, which is 1. The array length is 1, and we initialize even and odd to 0. Since there is only one element, we process index 0 directly. Here, even is updated to 1, the maximum of its current value and odd plus the current number. Odd remains 0, as it is the maximum of its current value and even minus the current number. After processing the single element, even is 1, and odd is 0. Thus, the maximum alternating subsequence sum for this example is 1. The time complexity of this solution is O(n), where n is the length of the input array, nums. This is because the algorithm uses a single loop that iterates over the array from the last element to the first. Since the loop executes exactly n iterations, we can directly associate its complexity with O(n). Within each iteration, there are two key operations, updating the even and odd variables. These updates involve taking the maximum of two values and performing basic arithmetic operations like addition and subtraction, all of which are constant time operations, or O(1). Combining the n iterations with these O(1) operations per iteration gives us a total time complexity of O(n). Importantly, this holds true for all cases whether the input is already sorted, completely random, or in any other arrangement, because the loop structure and the number of iterations are independent of the input's content. The space complexity of this solution is O(1), as it only uses a constant amount of extra memory, regardless of the size of the input array. To achieve this, the algorithm maintains two variables, even and odd, which are used to track the maximum alternating subsequence sums for even and odd indices, respectively. These two variables are the only significant memory allocations throughout the algorithm, and since they are simple integers, they occupy a fixed amount of memory. Additionally, no extra data structures, such as arrays, stacks, or hash maps, are created, and the input array itself is not modified, meaning no additional space is required for storing intermediate results. Even the loop counter, I, uses a constant amount of space. As a result, the algorithm's total auxiliary space remains constant at 1, making it highly space efficient. A comparison with the brute force approach highlights the efficiency of this optimized solution. The naive method would involve generating all possible subsequences of the array, which is computationally expensive because the total number of subsequences for an array of length n is 2 to the power of n. Evaluating the alternating sum for each subsequence would further require n time, leading to an overall time complexity of 2 to the power of n asterisk n. This exponential growth makes the brute force method infeasible for larger inputs. In contrast, the optimized approach leverages dynamic programming principles to track the maximum alternating sums at each step using only two states, even and odd, without explicitly generating subsequences. This drastically reduces the time complexity to n, and the space complexity to 1, making the solution both time efficient and memory efficient. The mathematical foundation of this solution lies in the way it updates the even and odd variables at each step. These variables represent the maximum alternating sums for subsequences ending at the current index. The recurrence relations ensure that all valid subsequences are implicitly considered. Specifically, even is updated as the maximum of its previous value or the sum of odd and the current element, representing the decision to either skip or include the element in an even indexed position. Similarly, odd is updated as the maximum of its previous value or the difference between even and the current element, representing the choice to skip or include the element in an odd indexed position. These transitions systematically account for every possible subsequence, achieving this in n time without explicitly enumerating them. This combination of efficiency and mathematical rigor ensures the algorithm achieves the best possible time and space complexity for the problem. When solving this problem, there are several common mistakes to watch out for. First, it's important to distinguish between subsequences and subarrays. A subsequence can include non-contiguous elements selected from the array, whereas subarrays are contiguous by definition. Many users mistakenly limit their solutions to subarrays, which can result in missing valid subsequences and incorrect answers. Next, edge cases are another frequent source of errors. For example, arrays with a single element, arrays where all elements are the same, or arrays containing only negative numbers require special handling. Overlooking these can lead to runtime errors or incorrect results. Another pitfall is using a brute force approach to generate all possible subsequences explicitly. This leads to exponential time complexity, which becomes impractical for large input sizes and can exceed computational limits. Finally, the process of calculating the alternating sum requires careful attention to the sign pattern. A common mistake is forgetting to toggle the sign for successive elements in the subsequence, which disrupts the alternating nature of the sum and produces incorrect results. In addition to those mistakes, there are some technical considerations to keep in mind. For example, in languages like Java or C++, integer overflow can occur if you use data types like int instead of long when working with large input arrays. This is easy to overlook but can lead to unexpected behavior or incorrect results. From an interview perspective, it is vital to thoroughly understand the problem scope. Make sure to clarify whether the task is about subsequences, subarrays, or both, as misunderstanding this detail can lead to implementing a completely incorrect approach. Optimization is also key. Dynamic programming is a powerful tool for problems involving subsequences, as it avoids brute force enumeration by leveraging reusable patterns. Familiarizing yourself with common DP techniques, such as those used in maximum sum or longest alternating subsequences, is highly beneficial. Lastly, be mindful of the trade-offs between time and space. While brute force solutions have minimal space requirements, they are computationally expensive. On the other hand, optimized approaches like dynamic programming may need additional memory but offer significant improvements in runtime efficiency, especially for larger input sizes. This problem is closely related to several others, which provide excellent opportunities for practice and deeper understanding. For instance, LeetCode 300 focuses on finding the longest increasing subsequence. Like the current problem, it deals with subsequences rather than subarrays and uses dynamic programming for optimization. Another related problem is LeetCode 53, which involves finding the maximum sum of contiguous subarrays. While this problem restricts the scope to subarrays, it shares conceptual similarities and is a great way to practice optimization techniques. LeetCode 376, which focuses on wiggle subsequences, directly relates to alternating patterns within subsequences and is closely tied to the alternating sum concept. Lastly, LeetCode 368 explores the largest divisible subset, where subsequences follow a divisibility property. This problem is a great example of how dynamic programming can be applied to subsequence-based challenges, providing further insight into efficient approaches for solving these types of problems. There are also several alternative approaches to solving this problem efficiently. One option is to use recursion with memoization. Instead of explicitly generating all subsequences, you can use a recursive function to explore all possibilities while storing intermediate results to avoid repeated calculations. This approach significantly improves efficiency, though it requires additional memory for the memoization table. Another popular method is dynamic programming. Here, you can construct a DP table where each entry represents the maximum alternating sum achievable up to a certain index in the array. With careful design, this approach can achieve a time complexity of O(n) squared, or even O(n), with further optimizations. Finally, in some variations of the problem, a greedy approach might be applicable. For example, if the input array is sorted or specific constraints are guaranteed, a greedy strategy can provide an optimal solution with minimal computational effort. Understanding when and how to apply these different strategies is key to solving the problem efficiently and effectively. Great job! Today, we delved into the maximum alternating subsequence sum problem, reviewed a brute force approach, and discussed key insights to tackle this kind of problem. Keep practicing, stay curious, and remember, every problem you solve improves your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!